Uh, yes, class. Am I audible to all of you? Yahya, Amina, Zaina.
Yes, ma'am.
All right. So in the last class, we had started and stopped at this point. This was where we had derived the electric flux for a sphere, right? So we could conclude to the fact that phi is equal to q by epsilon naught. Now, class, from here only, I'll continue this theorem that we have, which is known as Gauss theorem. Gauss theorem basically says that electric flux, this is equal to 1 by epsilon naught times the total charge which is enclosed in a surface. Basically, phi is equal to q enclosed divided by epsilon naught. This is the Gauss theorem. This says that in a closed surface, whatever is the charge that is enclosed, 1 by epsilon naught times that charge will give us the electric flux. And this is valid for certain objects. You have certain properties, so that we'll be studying later on. Right now, let us just focus on the law. So what is this law? And this law proven, how can this law be proven? Through this only. This is the exact derivation for this. For the derivation, you can contact the above question. So see, what is the Gauss theorem? According to Gauss's law, electric flux through a closed surface is 1 by epsilon naught times the total charge enclosed by the surface. This is your Gauss theorem. What are the properties of it? I'll discuss it. Just copy down the law at least. Then I'll discuss the properties with you. All right, let us now come on to the properties of Gauss theorem, if you have written it. So see, first property is very simple. See, in the formula, when you see the formula of electric flux, what do you see? You just see it is Q divided by epsilon naught, right? That is whatever is the total charge enclosed divided by epsilon naught. And you already know what is epsilon naught. Epsilon naught is 8.85 into 10 to the power minus 12. So that is also a constant which is fixed. So what do you require to know? You just require the charge enclosed because epsilon naught is already a constant. So look, if I have this, suppose this sphere, a charge is present Q, and I have the radius R, what would be the flux when I'll be calculating? It would be Q divided by epsilon naught. If I double the radius, the same sphere I'm having, the same amount of charge I'm having, now I have doubled its radius. So see, still the flux would be Q by epsilon naught. If I have this rod, the length of this rod is L, the radius of the rod is R, so I have 2 pi RL, then I have this rod present and I'm still calculating its flux. So this will be still Q by epsilon naught. I have this random shape and the charge enclosed is Q. So I'll be having the flux as Q by epsilon naught. So this is how all the charges are present. And if all the charges are present, we have the different surfaces present. Different surfaces, they have the different values of radii, their dimensions are different, but still, can you notice we are getting the same flux everywhere? This means even if I make the shape different, if I change the shape, if the charge enclosed is same, my flux will come same. So flux is independent of the shape and size of the surface. We can see this, right? Because there is no radius involved, there is no volume involved, there is no surface area involved, correct? So electric flux is independent of the shape and size of the surface. This is the first point that we have. Second is, when I am using this, when I'm telling you the formula of Gauss theorem, I'm constantly saying that this is charge enclosed by epsilon naught, charge enclosed by epsilon naught. What is this charge enclosed? Charge enclosed means basically you have chosen a surface, and within that surface, the charge which you are considering should be enclosed. Means, suppose if I have this figure with me, and minus Q2 is present, plus Q1 is present, plus Q3 is present, plus Q4 is present, minus Q5 is present. This is the scenario of the charge which is present. I'll not consider Q4, I will not consider Q5. I'll be only considering Q2. I'll be only considering this Q2, I'll be only considering Q1 and Q3. Why? Because they are within the surface. So my total charge, or before the flux, I'll calculate the total charge. So before my total charge, I will be having, for the total charge, I would include Q1 minus Q2 plus Q3, these charges only. And for my flux, I will be using the total charge enclosed only. That is Q1 minus Q2 plus Q3 divided by epsilon naught. That is the total charge divided by epsilon. All right, so this is how we'll be considering the total charges divided by epsilon. Just see all the charges that are included within the closed surface area. Fine, charge? Do not include any charge which is present anywhere else. Just include these charges, because the definition and the law, you cannot change the law. Law has a particular statement, and that statement has to be obeyed. If the statement says total charge enclosed, so you will be considering the total charges which are enclosed within the surfaces. Easy. Now, next property is easier than this one also. It says that basically, if the flux's direction is outwards, it's a positive flux. If it is directed inwards, it's a negative flux. That's it. And you already remember this from your electric field lines also. What we have studied in electric field lines. We have seen in electric field lines that for a positive charge, we have the direction of the charge is moving away. And for negative charge, electric field lines are towards. Fine. So outward flux, this is inward flux. This is negative flux. This is positive flux. So just remember this positive. Remember this negative. One more property. There are just two more properties left. If electric field line is just crossing the surface, suppose I have this surface with me. Fine, I have this surface with me, and this is the electric field line. Instead of going inside it like this, instead of moving inside it like this is just crossing it like this. This is just crossing it like this. So what will happen? Are the actually field lines going inside? Will the field lines actually be going inside? No, the field lines won't be going inside. So in such cases, if electric field line is not going inside, you do not get any flux present, correct? If you do not have any electric field lines going within the surface, you will simply say the flux is zero. The second possibility here, if you go by the mathematical analysis, is that when you draw the area vector on this surface, when you draw the area vector on this electric field, it would be perpendicular. And what is our formula for electric field? See, this is my surface area, right? If I drop a perpendicular here, suppose this is the perpendicular n cap, it's making 90 degree. So here my theta would be 90 degree, right? Directs the angle between the electric field and the area vector would be 90 degree, class. Now see, when I will put E dot S, which is equal to E S cos 90 degree, straight away flux will become zero. So mathematically, you can say that theta is 90 degree. That's why you are getting flux as zero. Or you can simply say that electric field line is not crossing the surface. That's why our flux is zero. See, what was electric flux? Do you remember? We have studied that electric flux is number of field lines crossing the surface. So if the field lines do not cross the surface, we won't get any flux, right? So this is also one of the properties that will help your answer to get a conclusion, and it will ease it. Lastly, when we are talking about a dipole, this you all only answer. Please answer, class. This is a question put up to all of you. If we have a dipole present, what would be the flux according to you? According to whatever we have studied, what would be the flux according to you?
Zero.
Yes, Zaina, what would be the flux? If we have it, what would be the flux? Just answer in the chat column. Just all of you answer in the chat column. Give me a yes, class. Sorry, just I had to leave for a minute. Flux would be zero. Yes, correct. Mariam, Yahya, and Zyna, yeah. See, why would the flux be zero? See, we are talking about the electric flux when we have the total charge enclosed and the epsilon naught, right? So epsilon naught is a constant, so we don't need to worry about the epsilon naught. But when we are talking about the constant, look, when we have the total charge enclosed, minus q plus q would always give you zero. If total charge enclosed is zero, you will get the flux automatically zero. This is what you'll be having. Let us see one question which is left. Once you write down the properties, then we'll start the last topic, which is continuous charge distribution along with the applications of the Gauss theorem. Write down these properties. Any doubts you have, class, please let me know. Zaina, how was your exam? Just update me in the chat column also. Anything you found very difficult, please just update me about your exam. And anybody else also is having any exam in this week, please update me. I have to arrange your extra classes also. Please let me know. Mariam, your exams are upcoming. Just text me on WhatsApp when is your, or just text me here only when is your exam and what is the syllabus. Let us discuss this now. I think enough time is given. See, this says that you have a cube and you have to calculate the flux through the cube and flux through each face. See how to solve these types of questions when you have flux through the cube. What is the answer for the first part? At least the answer for the first part you should be able to give. Flux through the cube, entire cube. What is the flux? It's Gauss theorem only. See, flux through the cube will always be Q divided by epsilon naught. Secondly, it says flux through each face. Now, how to solve these types of questions? You will be getting these types of questions also. So this basically says that if flux through entire cube, see, flux through a cube is equal to Q by epsilon naught. So flux through it, this means a cube has how many faces? It has 6 faces. So flux through 6 faces is Q by 6 epsilon naught, right? So Q by epsilon naught, sorry. See, flux through one cube. This is Q by epsilon naught. So flux through 6 faces. See, 6 faces than a cube. Are these different? They are not different. If one cube is giving you Q by epsilon naught, so 6 faces will also give you Q by epsilon naught because both are the same. Do you agree till here? Flux through a cube is Q by epsilon naught. Or even if I want to replace a cube, I can replace it with 6 faces. Now, what is the question? Question says flux through one face. Flux through one face would be Q by 6 epsilon. And this is the answer. Tell me, class. Now is this question clear to all of you? You will solve the next question which is given. Write down this and tell me the answer for the next question. At least you can try this. Hemisphere related with sphere. For a complete sphere, if this is, so for hemisphere, what would it be? At least second question you should all answer. Khadija, Mariam, Amina, Nuha, Rishita, Yahya, Zaina, Siddiqa, Soha. Please answer the second question. So Zaina's answer is correct. See, all those who are answering Q by epsilon naught. See class, when you are answering Q by epsilon naught, that is for the total sphere. See, when you have the total sphere with you, the flux through a sphere, this is Q by epsilon naught. Correct class? And when we talk about hemisphere, hemisphere means two spheres. So this means flux through two spheres. Basically, flux through a sphere is this. So this is flux through two hemispheres. If I write a sphere or I write a hemisphere, both are the same. So this is also two hemispheres will be Q by epsilon naught. So flux through one hemisphere, it would be Q by 2 epsilon naught. Quickly write this, then one last question we have to discuss this. Write it.
Ma'am, could you explain this question again?
Yes, see, we have given to find out the flux through a hemisphere. Now, two halves of a sphere, that is two hemispheres, they make up the one sphere. So when you have a sphere, we say the flux through the sphere would be Q by epsilon naught. Agreed? Right?
Yes, ma'am.
Yeah. All right. So instead of saying a sphere, if I say two hemispheres, two half of spheres, two hemispheres, that is equal to a sphere, right? Do you agree till here?
Yes, ma'am.
So if flux through two hemispheres is Q by epsilon naught, so through one would be Q divided by 2 epsilon naught. Clear?
Okay, ma'am. I understand.
This is the y-axis. Just make this as y-axis. C class, now you have this cube which is located at a distance from the origin, and this is having the side A also. Now electric field is given alpha x to the power half. Now electric field exists along x-axis. You have to calculate the flux of the cube and the charge. So see what we'll do here when we are calculating the flux. We have so many areas present, right? Firstly, before a calculation of anything, let me tell you. Flux is electric field dot the surface area. Now we have what all surfaces we have. We have 6 faces of a cube. Now look here. This face, this is the right face. So when I will drop n vector from here, n cap, electric field is directed towards the x-axis. So I know electric field is directed here. Look, electric field is directed towards the right. N cap is directed towards the right. Angle is 0 degree. I will get a flux from here from the right surface. Similarly, I have this left surface present. I have this left side. So n cap will be here. Again, electric field is towards the right. N cap, just see this surface. N cap will be towards the left. So left surface will also be there when I'll be considering. But look at the other surfaces which are present. If you look at the other surfaces which are present, look here. Above surface. When I will drop a perpendicular, here n cap, can you tell me n cap and electric field, what is the angle made between them? Electric field and n cap. 90. Yes, correct. This is 90 degree. So directly it would become 0. If you look at this face also, the back face, that its n vector will again make 90 degree with electric field. Similarly, this front face, this will also make 90 degree with electric field. This bottom face, even if you're talking about the bottom face, that will also make 90 degree with electric field. So basically, you have two faces left and the right left. N cap and N cap, left and right, both of these are present. So for the right surface, let us first calculate ER, surface area R. So what is the surface area? See, side is A. So if you have this is A, this is A. So for a square, what is the surface area of a square? What is the surface area of a square? Yes, Khadija? Mariam?
4 into sides.
4 into sides would not give you the surface area. That would give you the periphery. Yes, Khadija? Surface area?
6
Area of a square. How do you calculate?
Side into side.
Side into side. Very good. So this is A square. Correct. And where is the n cap pointing? Towards the right hand side. That is the x-axis. So surface area would be A square I cap. Fine. Come to electric field. What is electric field? Electric field is alpha x to the power half I cap. Why I cap? Because it is situated towards the right hand side. Now look, what is the x separation? When we are calculating, what is x when we are talking about it? See, this is 2a. Can you see from the origin to the right hand face, the total separation, this total separation when we are calculating, this is 2a. So x would be here 2a. So this is alpha 2a to the power half I cap. Or electric field, I can write this as alpha root 2a to the power half I cap. Now multiply both of these. flux would be alpha root 2 a to the power half I cap dot. What is the surface area? A square I cap. So once you multiply, you get alpha root 2 a to the power 3 by 2. This is the flux of the right phase. This is just the flux of the right phase. When we'll come to the left phase, see, surface area will still be a square, but area vector is pointing towards the negative x-axis. So the surface area here for the left surface, the surface area for the left surface, this would be a square but minus I cap. And what about the electric field of the left face? Alpha x to the power half I cap. You have C x, separation of left face from the origin. It is just A. Right face was separated by 2A. Left face is separated by A. That's why x here was 2A. X for the left face is A. Tell me this, the substitution of electric field is clear to all of you, or should I repeat it? Clear or not?
Ma'am, can you repeat it once?
I'll repeat it. See, when you are putting the value of x, see, electric field is given alpha x to the power half. X means a separation from the origin. So for the right face, this is the point of separation. This is separated from the origin by 2A, A plus A. If you look at the left face and the origin, this is just separated by A. Now clear?
Yes.
So this would be, left side would be alpha, A to the power half. So once you take the flux, it would become alpha, A to the power half, I cap dot A square minus I cap. So this becomes minus alpha A to the power 3 by 2. Now see, when we are calculating the total flux would be the right phase flux from the left phase plus flux from the top phase plus flux from the bottom phase plus flux from the front phase plus flux from the back phase. Right is alpha root 2 a to the power 3 by 2 we have calculated. Left is minus alpha a to the power 3 by 2. Rest all of these are plus 0. So what is the total flux? Total flux is root 2 can be written as this can be written as 1 minus root 2. So 1 minus 1.41. You can write this as 0.4, right? Root 2 is 1.41 and 1.41 minus 1 would be 0.41 something. So this is 0.4 alpha a to the power 3 by 2. You can leave it at this step also. This is the flux, but the question asked us to calculate charge also. If flux is charge enclosed by epsilon naught, so charge enclosed would be flux into epsilon naught. So charge, when you have the flux with you, so charge enclosed would be 0.4 alpha a to the power 3 by 2 multiplied to 8.85 into 10 to the power minus 12. This is how you will be calculating. This is from the charge. Write it down. First, write down this. Okay, yes, Zaina.
Thank you, ma'am.
Now, continuous charge distribution basically means on a straight line, how much charge is distributed, or on a surface area, how much charge is distributed, or on a particular volume, how much charge is distributed. So if we have linear charge density, basically this is the charge distribution in one dimension. Means that you have the total charge, you have the total length. So linear charge density basically means charge per unit length. This means that charge per unit length. So we represent it by lambda. So we write this as Q divided by L, which is here, this is charge and this is length. This is important for your applications of Gauss theorem. We have to start with applications of Gauss theorem. For that, this is essential. So SI unit and everything you can conclude. What would be the SI unit? Coulomb divided by meters. And if this is variable, so this will be dq over dl, like this. Look at this question. This says that charge of 10 coulomb is uniformly distributed on a wire of length 5 meters. Linear charge density. Lambda would be charge divided by the length. Charge is 10 coulomb divided by the length is 5 meters. So this is 2 coulomb per meter. This says that charge on 2 meter length of wire. See class, if this, what is this saying? This is saying on 1 meters, you have 2 coulomb. So on 2 meters, you would have 2 into 2 coulomb, right? That is 4 coulomb. Correct. In 1 meter, we are having 2 coulomb of charges. So in 2 meters, we'll have 4 coulomb of charges. That's the answer for the second part. Easy. This is easy. You'll be able to manage. Write it down quickly.
Ma'am,
Yes. Say.
are you taking 2 hours today?
Yes, yes.
Okay, ma'am. Can you explain this topic again? Actually, I by mistakenly left the meeting.
Okay, see, Mariam, this basically is about the charge distribution. So if we have linear charge distribution, you have superficial and you have volumic. So in one dimension, basically charge per unit length is what we call as linear charge density. That is how much charge is distributed on 1 meter length. So this is the formula. We represent it through lambda. Lambda is equal to Q by L. That's it. So if the SI unit would be coulomb per meter, And the differential, if you want to differentiate it, that would be dq over dl. That's it.
Okay, ma'am. Thank you.
See, this says that linear charge density of a wire lambda is 2x. Now see, this is variable. If it was constant, we would have used the normal division, but here it is variable. So for variable, you will differentiate. You will perform differentiation. So what is differentiation of lambda? Dx over dt. But see, do we require dx? Right now we have lambda with us. We require dx. So how to, sorry, not dx, dq. So if we require dq, what we'll do? What is the inverse function of differentiation? It's integration. So dq is equal to lambda dt integral. Because we do not require this. This is already given to us. We require this. So when you will integrate this, you have q with you. Lambda is 2x dx, not dt. Charge per unit length, hai na? So this would be dx. What have I written here? Yeah, dq over dl, yes. So this would be integral. So this becomes 2. This becomes x square by 2. Are there any limits given? On 10-meter length of wire, yes. So 0 to 10. 2 gets cancelled. 10 square is equal to 100 Coulomb. Write it quickly, then we'll see superficial charge distribution.
I'm going to explain this question again, the integration part.
Integration, this is 2x dx. What is the formula for integration? What is the generalized formula?
So, ma'am, we were not taught the basics of integration and differentiation in class 11th.
Yes?
Actually, we were not taught the basics of integration and differentiation in the class 11th.
Okay, I'll repeat. Though we have done this in this batch, I think, Mariam, you were not present that time. We have actually revised the entire integration, differentiation, and vectors in this batch also. Anyways, this is x to the power n. So how do you integrate it? X to the power n plus 1, you write it, and divided by n plus 1. So you have two constant here, 2 I have kept aside. X to the power 1, 1 plus 1 would become 2, divided by n to the power 1. Means whatever power you are getting right now, divided by the same. Fine? X to the power n plus 1 divided by n plus 1. Here our n was 1. So it became 1 plus 1, 2 divided by 2. Then what we do, suppose the powers we have to integrate it from x1 to x2. So whatever is the power now obtained, we put the upper limit first, then subtract and put the lower limit with the same power. So that's why 10 square minus 0 square we have. Fine. This is 10 square because this is the upper limit in place of this x, minus 0 square, which is the lower limit. That is equal to 100 in this case. Is it better now, Maria?
Yes, ma'am, I understood a bit.
Okay. Let me know if you have any query. I'll share the videos also of the bridge course that we had. Fine, that will help you.
Okay, ma'am.
See, next is superficial charge distribution. This is the charge distribution in 2 dimensions, basically. You have this in 2 dimensions. So whatever is the charge per unit the surface. I have taken those classes, Mariam, actually in this batch. I'll take your classes separately because in this batch already because of those classes, the syllabus is being delayed. So I'll take your separate classes. I'll share the video lectures of this with you, the bridge course that we had. Basics of integration, differentiation, and vectors we have discussed. So that I'll share you the video. And then also if you have any doubts, I'll take your class separately then. Okay, just remind me once, Mariam. I'll take your class.
Okay, thank you.
So surface area is S, charge is Q. So here the surface charge density is represented by the symbol sigma. This is charge per unit, the surface area. This is for constant values. If you have variable, then that is dq over ds. This is for variable. You will be using all these in the applications of Gauss theorem. So this says that charge of 10 coulomb is uniformly distributed on a surface of a sphere of radius 2 meters. So easy. See, you have a surface charge density. What is the charge? Charge is 10 coulomb. What is the surface area of a sphere? You have to write just the surface area. So 4 pi r square. This much coulomb by meter square would be the. And the second part says if in 1 meter square, we are having 10 divided by 16 pi. So in 2 meter square, we would have just the double of it. 2 meter square would be 2 into 10 divided by 16 pi, which is equal to 10 divided by 8. Fine. Write it quickly. We'll then see volume and charge distribution. Last one, volume charge distribution, volume per unit charge. It means this is in 3 dimensions. So volume charge density, when we are talking, see, this was represented, this was represented by lambda. This is represented by sigma. And this is represented by rho. This is represented by rho. So you have volume per unit charge which is present. This is again for constant. If you want to write it for variable this way, dV over dq. So this says that 10 coulomb of charge is present on a radius of 3 meter. So see, volume charge density rho. Volume charge is 10 coulomb per volume. Volume is 4 by 3 pi r cube. 3 whole cube. So this is 10 by 4 pi into 9. Now this says charge on 3 meter square. So this is a coulomb by meter cube. So in the second part, this says that for 1 meter cube, we have 10 by 4 pi 3 into 3. So for 3 meter square, it would be 10 divided by 4 pi 3 into 3 into 3. That is 10 by 12 pi. Write this quickly, class. All right, class. So all of you, if you have completed till here, you can start leaving. Now, just one last topic is left: applications of Gauss theorem. That I'll complete in the next class, and I'll start with electric potential only in the next class itself. So let's meet on Thursday now. Please revise and come. Be prepared. All right. So you all can leave if you've completed. Thank you so much, class. Bye.
Thank you, ma'am. Ma'am, can you explain this question once again?
Yes. See, Mariam. This is rho. Rho means the charge per unit volume. How do we write the volume of a sphere? 4 by 3 pi r cube. This is the formula. So 4 by 3 pi r cube is the volume. 10 is the charge. So charge per unit volume is this. This is clear?
Yes, ma'am.
So this is coulomb per meter square, a meter cube. It means in 1 meter cube, this much of charge is present, right? In 1 meter cube, this much of charge is present. So in 3 meter cubes, how much charge would be present? Just multiply it
Into
with
3.
unitary method that you're following, correct?
Yes.
All right.
Thank you, ma'am.